So this is the last topic, which is enthalpy and internal energy. Enthalpy, we are using the symbol H. Internal energy, we're using the symbol E. The enthalpy is related to internal energy, but also you need to consider the extra energy coming from their volume and the pressure they are exerting. Okay, so this is sort of the everything considered. Okay, the internal energy is essentially actually internal energy, related to the temperature, but the pressure and the volume is also part of the energy, and you have to combine them together. And this is how enthalpy is being defined. And then let's read the problem. And problem says, okay, there is a reaction, and for that reaction, delta H is given. And then they ask you, what's the value of delta E? I give you the delta H. Okay? So the problem is actually misleadingly simple, and then the problem is actually not that hard if you understand exactly what this means. Okay? So let me actually complain about this information. Okay, I know delta H is certain energy, I got that, but what is this? Is it per mole basis, or what is that energy has related to this reaction? Okay, and so I'm going to write this with this comments that is actually pretty, in a way, very funny. Okay, but I love to write this. Okay, so let me write it down. Delta H for the reaction written as it is. Okay, so the whole thing is essentially means all the people do not write, and this is what people typically say per reaction. Okay. So going back to this original complaints, I don't get it what this energy is really related, and now I'm trying to say that when chemists write this way, that means this energy changes specifically for the way that you write the reaction like that. Okay? So let me give you a related example. If I write this equation as NO2, N2, and half oxygen, this number is half now. Okay? So this number is depending on how it is written. Okay? So let me recap it one more time here. So I think that's the one perspective. The second perspective is delta H is 163.14 kilojoule. What's that means? Yes, okay, it's a minus 163.14 kilojoule per reaction. That's what I said here. That means when 2 moles of N2O So now I think that this one starts to make sense now. This energy just given as it is, because I look at that, when I use 2 moles of this compound, this amount of energy is going to be liberated, because I guess that is an exothermic reaction. So that energy is corresponding to actually 2 moles of NO2. Right? Also, you can see that producing 2 moles of N2 while producing 1 moles of oxygen, and that's how related. So there are 3 statements that equally make sense. When 2 moles of N2 produce, or 1 mole of oxygen gas produce. Okay. So they want to say all this case is, so they cannot write anything, just give you just the energy as it is. Because you give this, all the information was given in the form of an reaction as written as it is. So that's the first thing. Let me do the second one. So that's number one. Number two is delta E was, they want to know what's delta E, but given that delta H was given. And these two quantities are related. And as you see here, this is how you can start from here. So now what you can do is, I guess a change in the delta H, the same as change in the delta E plus change in the delta PV. That's the one way to do it. Another way to do is, well, I think that I know this P times V is nRT based on the ideal gas law. So I can rewrite this equation now to H equal E plus PV now is E plus nRT. Okay? So I just changed the form of the relationship from the PV. Instead of dealing with both pressure and volume, I just deal with the temperature. And when you read this problem now, let's read the problem. What's the value of the delta E for decomposition of certain grams of NO2 at 25 degrees C? So immediately 25 is okay, I should not 25, 298 Kelvin, so 298 is a temperature that I will use. What that implying it is, this is an isothermal situation. Okay, your temperature is maintained to be the constant. Okay, so therefore, if this equation change it into delta H, so delta E plus, because these two are constant, so only thing that changes is delta N, and then RT remains. So it's a delta N times RT, and that's how this is related. And then let me pay attention to this reaction. You see the information of gas here, and gas. When we say this equation, I only count the gas. If you see the liquid, ignore that because it does not occupy too much volume. It's a small quantity that you don't have to consider. So all I need is, I'm just looking at the gases and count how many moles involved before and after. So it's always final minus initial, right? It is so obvious, but it's good practice for you to know. And the number of small final, which is your product side, 2 plus 1, that's a 3. And the before, just a 2. So 1 mole. So there's a change of 1 moles of gas. So this is what it really means. 1 moles of gas is your delta N, and that's something that you're going to put it in. So I think I'm ready to answer that. Delta E is delta H. Now I'm going to flip this equation shown up here, minus delta N RT, and the delta H was minus 163.14 kilojoule minus 1 moles. And then because I choose to use a joule, 8.314 is my choice. And then 298. Okay. I think I finished it, except for one minor detail, and the minor detail is actually you have to be very careful. Okay, this thermodynamics class I taught many years. The more I teach it, I emphasize pay attention to the units of each quantity you're adding to, you're subtracting to, you plug it in. So let's look at that. You are not comparing apple to apple here. Maybe apples. It's not even apple to apple. This is more related to oranges and tangerine. Probably that's a better analogy. Because why I'm saying this is this number was given as a kilojoule here, right? What is a unit that you're going to put it in? nRT. What kind of number with what unit that you're going to have? I mean, I can calculate the numbers, but what's the unit resulting you are multiplying those numbers? Simply joule, right? So what you need is, because remember, this one was actually joule per mole Kelvin. Remember that? So that's a mole, goes away, Kelvin goes away, only the joule survive. So whatever the number it is in the unit of joule. So this is an orange and this is just a tangerine, right? It doesn't make sense. So all you gotta do is, well, I'll just make it up. I simply multiply by, do that. And you can simply make sure you put a say, I know what I'm doing. It's a kilojoule in that unit. And then you're pretty much done and ready for plugging into your calculator. All right. And then what do you have? Minus 165.62 kilojoule. Okay. So I'm going back to actually my the initial comment. So whatever this number was given, that's per reaction. All I did is delta H per reaction. That's all I did. And then I have to really answer the specific question regarding to the system 186 grams of this gas. So I'm using that information, but that's not the answer. The real answer is I'm looking for is different. So to make it clear, this is still I'm dealing with per reaction written as it is. So therefore, and what that means is the one that is relevant is actually when you have 2 moles of N2 gases reacted, and that's the information when we say per reaction. Okay, so I came here and let's go back to the problem. Say we are dealing with 186 grams of NO2, and I need to convert that into the mole. And here I have given you the molar mass of this. So what that means is 186 gram N2O, that is your system, is 186 gram multiplied, converted into a mole. 44.2 gram, 1 mole. Right? You can now convert that into a moles of NO2 gas. What's the number? That's a 4.23 mole N2O gas. That's more useful term than the gas. So then what do is this is a delta E for 186 grams of N2O. Just want to make sure that we are dealing with a specific, and this is per reaction. So this is the one that we want to answer. That is okay. This is a 4.23 mole N2O gas, and then okay, and then from what I learned from it is 2 mole of N2O. The delta E is 165.62 kilojoule. Okay, so I use that information. I just calculate per reaction, and then I put the size of your system and multiply that, and nicely this one goes away. And now you can calculate this number. That is minus 350 kilojoule. Okay. So that's the first question that I've shown you. And essentially, it all started with this information was provided as a delta H, and this was given as it is because your reaction was written in this way, and using that information you can calculate for system-specific quantities, and you can calculate for internal energies. Even for delta H's, you guys can calculate the same thing as a delta H for that system, multiplying this by, I guess, this number divided by 2 moles of reactant, and that's what's there. Okay, so that's the first question, and then actually there's an extra question here. So the extra question is now, assuming delta H is still same, do not change the temperature, means I can still use the same number as it is. But what about the delta E for the same system at 217 degrees C? So, so now the temperature used to be 25 degrees C. Now temperature is 217 degrees C. But you know, temperature is actually always has to be written in numbers with a unit of Kelvin. So that therefore this one is 217 plus 273. I think that's a full 10. 490 Kelvin. So all has been changed is nothing but the temperature has been changed. So they want to know delta E first. I want to know delta E first. So delta H per reaction minus delta N times RT. And then I can use the same number, 163.14 kilojoule minus 0.082, temperature 9490, and make the unit of kilojoule. So I just multiply by 10 to the minus 3. It's a kilojoule. So by doing so, you'll get the new number now, 167.21 kilojoule. And that's the answer is, it is, but this information, I always build a habit of putting